Hello and welcome you all to the third lecture on the electroweak interactions in standard model of particle physics. And if you remember, in the second lecture we actually defined the special theory of relativity and Lorentz transformation in particular, and argued that how objects can be invariant under Lorentz transformation. And in today's lecture we are actually going to derive something called Lorentz invariant phase space. Now, this plays a very important role in particle physics because the laws of particle physics are tested in different experiments where particles actually are getting created or annihilated or decay. And in all these cases, there is a part which is called the phase space, which plays an important role. And in today's lecture, we are actually going to see that how it can be manifestly Lorentz invariant. So, that is the part of today's lecture. So, let us get started. So, the very notion that physics will not change in different inertial frames, the relativistic formalism applies, and it says that the potential laws of physics will therefore need to be manifestly Lorentz invariant. So, this is one very important principle which we are going to abide by. And as I just said that in particle physics, the principles of fundamental interactions, particle interactions via strong, weak and electromagnetic interactions in particular, thus can be identified from different reactions which the particles undergo, and this gives rise to what you call the cross sections and decay widths. Now, the cross section and decay widths can be systematically calculated from the quantum field theory, which is the basis of particle physics, okay, using something called the S matrix formalism. Now, if I have to discuss that, that's a bit of long story and I cannot really afford to do so. What we are going to do, that we are going to adopt a different route and essentially arrive to the Lorentz invariant phase space in particular from what we call non-relativistic approach. So, this is going to be our approach. So, if you want to look into the details of this approach, I am actually following the book of Mark Thompson. So, you can also do that. Okay. Now, the point is the cross sections and decay width or the transition from one state to the other is essentially governed by what we call the transition probability rate, and transition probability rate of course associates two states, one initial state and the other final state. So, it is a transition from state I to state F, and this transition probability rate is identified with what we call the gamma Fi, and it is given by Fermi's golden rule. Now, what does it say? The Fermi's golden rule basically says that this gamma Fi is equal to 2 pi into mod of T Fi square into rho Ei. Now, what are these quantities? First of all, I must mention that this actually is using the natural units, which is h cross is equal to c equal to 1. If you invoke those, there are some h cross like 2 pi by h cross is there, which I am not writing. Now, what are the different quantities that we have here? This T Fi square is what is called the transition matrix element square. This is called the transition matrix element, and the square of that is actually included in this one, and this rho Ei is the one that we are going to discuss in most glorious details today, and this is what is called the phase space or density of space, phase space. All right. Okay. So, this is what is the transition rate from state I to state F given by Fermi's golden rule, which basically has two components in it, one which is the transition matrix element and the other is the phase space. Okay. So, what is the transition matrix element? Now, this transition matrix element or whatever we call TFI, it is basically the sandwich of state F and I with the H prime, which is called the part R being Hamiltonian, which is causing this transition from state I to state F, right. So, this is what you actually have. So, the total Hamiltonian is H equal to H naught plus H prime, and the part R being Hamiltonian is the one which causes this transition from state I to state F. So, the first order term is essentially F H prime I. What will be the second order term? The second order term will be the sum over all intermediate states through which the transition may occur. So, this will be the F H prime k, k H prime I by E I minus E k, where k must not be equal to I. Okay? And this quantity TFI, the transition matrix element, as you can understand, is governed by the interaction Hamiltonian or part R being Hamiltonian, and that will essentially come from your fundamental particle physics or your interaction. Okay? So, this is something that we are going to discuss later. Okay? What we are going to discuss today is basically the other part, which is the phase space density or density of states. So, the rho EI, which is the other part in the transition probability, is defined as dN dEf, where dN defines the states which are available between the energy EF to EF plus dEf, and this has to be evaluated at the initial energy EI. Okay? So, that is what this quantity means. So, therefore, what we can do, that we can actually write this as an integral of dN dEf including a delta function which ensures the energy momentum conservation, like energy conservation rather, delta of EI minus EF dEf. Now, once again you can see that this integral of the delta function with the measure as dEf basically ensures that you evaluate dN dEf at the value EI, which is the definition of rho EI. You can also say that this is nothing but the integral of dN, the states available between energy EF to dEf with the delta function delta of EI minus EF. So, if I now rewrite using this expression of rho EI, the expression of transition probability using Fermi's golden rule, what does it read? It reads like gamma Fi equal to 2 pi mod of T Fi square delta of EI minus EF into dN, and this dN is essentially the kinematics of the process. So, you can basically say that this has two parts in it. This part, the TFI square, this defines the dynamics of the process, like what kind of interactions and etc., the part having Hamiltonian or whatever that you want to say, whereas the dN, which is the phase space part associated with it, actually governs the kinematics of the process. And once again, we would like to reiterate that we are interested in calculating the relativistic formalism of the transition probability. So, this is what we actually require, because we have already sort of identified or established the point that the rate of transition from state I to state F requires to be obeying the special theory of relativity, or they need to be Lorentz invariant. Okay. So, now what we are going to do, that let us consider a process which is like A going to 1 plus 2. So, this is a simple process. You can say that this is actually a decay process, right. A particle decays into two particles 1 and 2. Okay. So, now if I have to kind of parameterize this decay using the transition probability of the Fermi's golden rule, which we just talked about, how do I write it? So, the first part, which is the transition matrix element TFI, that I am going to write as the psi 1 psi 2 H prime psi A, or in other way we can say that this is an integral of psi 1 star psi 2 star, the part having Hamiltonian, I do not know what exactly this is, h prime psi a d cube x, and this d cube x is essentially the volume where the wave functions are normalized. Now, this is the question that we would like to address here, that how exactly you do normalize the wave functions, okay? And we will use what is called the Born approximation. What is Born approximation? It basically says that the perturbations are assumed to be small, and so therefore, the initial wave function and the final wave function, the initial wave function of A, which is far from the happening place, that can be approximated by the plane wave solution. Now, I am sure all of you can tell me what is a plane wave solution. So, psi xt can therefore be written as A into e to the power I p dot x minus E t, correct? So, this is how we can actually write the plane wave solution using the first Born approximation. Okay. And of course, as you can imagine that this A which we have used is nothing but the normalization. Now, the question is what this A is, how do I normalize this? In quantum mechanics, you all know that this normalization plays an important role, and so is here. Suppose you are normalizing the wave function in a cube of a volume A. So, therefore, what you have, the integral is x equal to 0 to A, y equal to 0 to A, z equal to 0 to A, psi star psi, which gives you the probability density integrated over this volume dx dy dz is must be equal to 1. So, this is according to the total probability has to be conserved. So, therefore, you can say that if you have this plane wave function, so then this psi star psi will simply give you what? This will give you this factor of A square, and this volume integral will give you A cubed, correct? So, therefore, what you are trying to find out, the normalization in this particular case will be simply A is equal to 1 by square root of A cubed, or you can say that this is 1 by square root of volume V. So, this is the simplest way of saying that what the normalization constant is. Now, there is something more to this, because you are saying that I am normalizing this wave function to be remaining within this cube. So, there must be a periodic condition which we must impose on the wave function, which is to say that I want my wave function at this point of the box to be exactly identical to what I had at x, y, z. Okay? So, psi of x plus a y comma z must be equal to psi of x comma y comma z, and this is true in all directions. So, I can also say psi x y plus a z must be equal to psi x y z, and similarly psi of x y z plus a will be equal to psi of x comma y comma z. So, this is what we call the periodic condition on the wave function. Now, what does it imply? It basically says that because the wave function we have assumed using the Born approximation that it has a form like e to the power I p dot x minus E t. So, this periodicity which we have imposed basically tells me that e to the power I p x x must be equal to e to the power I p x into x plus a, correct? Similarly, I must also say that e to the power I p y y that must be equal to e to the power I p y of y plus a, and similarly e to the power I p z z must be equal to e to the power I p z z plus a, and this tells you that e to the power I p x a must be equal to 1. Now, how can I write it? The 1 can be written as this should be 2 pi nx. I can write it as a 2 pi nx, where nx is an integer. Similarly, I can say that e to the power I 2 pi a that must be also equal to 1, and okay, with a factor of I which I must not forget. So, this is e to the power I 2 pi nx. Similarly, e to the power I p y a is I 2 pi ny, and e to the power I pza is I 2 pi some other constant which is an integer number nz. Or rather you can say that px, py, pz, so therefore depends on nx, ny and nz, or you can say that px, py, pz is equal to nx, ny, nz into 2 pi by a, right. So, now the dqp, the volume integral dpx, dpy, dpz, that must be equal to 2 pi whole cube by a, or you can say that this is 2 pi whole cube, a cube is the volume of the cube which is equal to v with nx, ny and nz chosen equal to 1. So, this says a very important statement which is as follows, that the each state in momentum space basically occupies a volume of 2 pi whole cube by v. Now, we are going to ask this question that what is the number of state dn that we have between the momentum range of p2 p plus dp. Then you say, okay, this is nothing but essentially equal to the momentum space volume between p2 p plus dp, that is in the spherical shell with radius p2 p plus dp, and that must be divided by the average volume that is occupied by each single state, because we have already stated that each single state in the momentum space basically occupies a volume of 2 pi cube by v. So, therefore, I can say that the dn is nothing but the momentum volume of the spherical shell between p to p plus dp, which is 4 pi p squared dp, divided by the volume which is occupied by each state, which is 1 by 2 pi cube by v. So, therefore, you can simply say that this is d cube p, which is 4 pi p squared dp into v by 2 pi whole cube. On the other hand, I can also say that this dn dp is essentially 4 pi p square by 2 pi whole cube into v, or you know rho e, which is there in the Fermi's golden rule, is dn de, which you can say that this is dn dp into dp de, and this can be calculated for any particle that is being produced. Okay. So, provided you know how dp de is there. So, this is 4 pi p square by 2 pi whole cube v mod of dp de. All right. Now, there is one part which actually makes us a little worried, like this volume v, like the volume which we normalize the wave function with, how that can appear in your decay rate or your cross section calculation. And it turns out that it actually nicely gets cancelled with the transition matrix element square, and it is going to be true for any kind of final state and any kind of initial state, and this must be the case that the volume factor actually gets cancelled. So, therefore, what we can do, so this is something that we can do a couple of exercises or homework exercises, tutorial exercises we will actually have. But for the time being, what I am going to do, that I am going to ignore this volume factor and then argue that this density of states or the number of states between momentum p to p plus dp is dn equal to d cube p by 2 pi whole cube. So, this factor of 2 pi whole cube is essentially coming from the finite volume of each state in the momentum space. Okay. So, now if you have different independent momentum states, they will actually have separate dni, right. So, if you have basically n body decay, that is n body final state, there are n minus 1 independent momenta. Why n minus 1? Because there is a momentum conservation with respect to whatever initial state that is actually generating the final state. So, therefore, you say that for capital N body decay, your dn will be essentially given by pi of I equal to 1 to n minus 1 dni where this d and I is nothing but d cube pi by 2 pi whole cube. Or you can say that I can also rewrite this as I equal to 1 to n minus 1 d cube pi by 2 pi whole cube into a delta function which ensures a conservation of momenta delta cube of pa minus sum over I equal to 1 to n pi with a measure d cube pn for the nth final state. Or in other sense, you can say that this turns out to be 2 pi whole cube into pi equal to I equal to pi of I equal to 1 to n d cube pi by 2 pi whole cube with the delta function delta cube of pa minus sum over I to n pi. Okay? So, this is how the phase space actually looks after adhering to the fact that each state in the momentum space occupies a volume of 2 pi whole cube by v. Okay? So, this is what happens to the phase space part of the transition probability. Now, there is an important point that we are going to stress upon. The point is as follows, that the wave function normalization, the way that we have actually done in a volume of cube, okay, this is not manifestly Lorentz invariant. So, we are stating that wave function normalization to a particular volume V is not Lorentz invariant. Now, this is easily understood from the fact that when this volume actually moves with a very high velocity in a different frame which is moving with a high velocity, the volume essentially will be Lorentz contracted. Now, this is one of the immediate corollaries of the special theory of relativity, that if you are running with a very high speed, then the length in that direction actually gets contracted, and this is what is called the Lorentz contraction. And this contraction will be a factor of 1 by gamma. Remember that we actually devise this quantity like gamma, which is like square root of 1 by 1 minus beta square, where beta is essentially defined as v by c. In the c equal to 1 unit, you can treat beta equal to v. Okay. So, this is going to shrink along the direction of the relativistic motion. So, if this is your box with which you normalize the wave function with side A basically. Now, if this is moving along with a velocity v along this x direction, this length is going to get contracted to A by gamma. So, this is what is called the Lorentz contraction, and this motion is actually with a velocity v, which you can parameterize with beta c. Now, let us look into this fact that if you have one particle per unit volume, then this volume which is actually 1, this will be defined as n by a into 1 by a square, essentially n by a cube, which I have kind of segregated the 2 dimension. This is actually the a square which is perpendicular to the motion. So, this is like 1 by a square, and this is the 1 by a factor which we actually have along the direction of the motion, or in a sense you can say that this n is equal to a cube. Now, suppose you are actually doing it for this relativistic guy, then how should you do? Then this should be n by a by gamma into 1 by a square, because this dimension does not change. So, that turns into what? This turns into gamma into n by a cube, and this is actually equal to gamma. Now, you also recall that E is equal to actually mc square, but that m is the rest mass. But now, if you want to convert it to the relativistic mass, then basically it becomes gamma m into c square. So, E is equal to gamma m into c square, where m is the relativistic mass, or in the units of c equal to 1, you can basically say that E is equal to actually gamma into m. So, therefore, what you are trying to say is that this gamma, which is actually E by m particles per unit volume in the boosted frame or boosted volume, that actually appears. Okay. So, if you have this motion, then basically you have this kind of a relation, that n by A by gamma into 1 by A square is equal to gamma, which is actually E by m, these many particles per unit volume. Okay. So, therefore, what we are trying to say is that the Lorentz invariant choice of normalization of the wave function must therefore be proportional to energy E particles per unit volume, so that the increase in the energy accounts for the effect of Lorentz contraction. So, in a sense, we will say that the way that we were normalizing in the non-relativistic case was basically psi star psi d cube x equal to 1. But now what we are going to do, that instead of doing this, we are going to rewrite this as psi star x, psi prime, let us define that wave function in the relativistic case as psi prime star x, psi prime x d cube x, and this is, we are arguing that this must be equal to the energy to actually comply with the Lorentz contraction. So, this factor of E is something which was apparent from this expression, because it was a factor of gamma which is coming actually, but why this factor is 2E, we will come to that in a moment. Okay? So, this is what we are defining, that the Lorentz invariant way of normalizing the wave function must account a factor of 2E on the right hand side. Why this factor of 2? I am going to come in a moment. So, now if I ask you that how therefore the relativistic wave function is actually related to the non-relativistic wave function, you say that this is very trivial. This psi prime x, which I defined right here, must be equal to 2e whole to the power half into psi x, correct, where psi x essentially defines the wave function in the non-relativistic case. So, this is what the definition that we actually have. All right. So, now let us try to define the Lorentz invariant matrix element for a process in general A b going to 1 plus 2 plus blah 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 n. So, from our definition, this mfi, so I am changing the notation from tfi to mfi. So, remember earlier I defined the transition matrix element as tfi, but when I am actually adhering to a Lorentz invariant matrix element, I am actually defining it in terms of mfi. Now, this mfi will be simply the sandwich of psi 1 prime, psi 2 prime, which are the final state wave functions, with this perturbing Hamiltonian with the initial state wave functions psi a prime, psi b prime, etc. Now, if I want to rewrite it in terms of the non-relativistic wave function, then each of this wave function will have a factor of 2e whole to the power half, as we just noted above, right. So, using that we can say that this will be 2e1 2e2 into 2ea 2eb whole to the power half into tfi. So, therefore, now if I want to rewrite the Fermi's golden rule, which we wrote actually for the process of a decay A going to 1 plus 2, this gamma fi turns out to be, so this was the definition that we actually had, that gamma fi was 2 pi into mod of tfi square into rho ei. This rho ei, the phase space part, we said that this can be written as a delta function of ei minus ef into the phase space density dn. Okay? And we already derived that this dn, this phase space for this two body decay in particular, this will be simply 2 pi whole cube into pi of 1 to 2 d cube pi by 2 pi whole cube into delta cube of pa minus p1 minus p2. So, this ensures the momentum conservation between the initial and final states. So, let us put this dn back into this expression and let us rewrite the gamma fi. So, this is going to turn out, so this 2 pi whole cube multiplied with this 2 pi becomes 2 pi whole to the power 4. This is integral of tfi square, and then this delta ei minus ef, that is actually delta of ea minus e1 minus e2, and there is a function of delta cube of pa minus p1 minus p2, and then there are these phase space functions like d cube p1 by 2 pi whole cube into d cube p2 by 2 pi whole cube. Okay? Now, let us rewrite this whole quantity in terms of Lorentz invariant matrix element. Now, if I want to do that, you remember what I defined, that if I want to rewrite this whole thing in terms of mfi square, the relation between mfi square and tfi square will be what? This will be related with the energy 2E1, 2E2 into 2EA. So, the relation between this, for this particular process A going to 1 plus 2, the mfi square will be related to tfi square by 2E1, 2E2 into 2EA. Or in other words, you can say that this tfi square should be equal to 2E1, 2E2, 2EA whole to the power minus 1 into mfi square. Now, what I am going to do, that I am going to put this equation back into the expression of gamma fi, and if I do that, what I see, I had this expression of 2 pi whole to the power 4, but then now there is a factor of 2EA which comes out of the integral, because my integral is essentially on the final state particles momentum, right. And then instead of tfi square, I write mfi square, the delta functions are there, delta EA minus E1 minus E2, delta cube of PA minus P1 minus P2, and now here this d cube P1 by 2 pi whole cube, this is aided with another factor of 1 by 2 E1, and this d cube P2 by 2 pi whole cube is aided with additional factor of 1 by 2 E2. Okay. So, in a sense you can say that this phase space parts, the phase space densities or the phase space integrals, whatever that you want to say, that was d cube pi by 2 pi whole cube, but once we actually inserted what you call the Lorentz invariant matrix element square in the transition probability, this integral has changed into something like d cube py by 2 pi whole cube into 2EI. Okay. So, I think this will be a good point to stop. Okay. So, we can carry on in the next class.